Let us now look at the steps of the design methodology in detail. The design methodology begins with the requirements elicitation step. This is largely a research exercise, which may even involve hiring a consultant to gather information for potential clients. The idea behind this, the objective of the step obviously is to acquire as comprehensive as possible a statement of requirements from the system that has to be designed. It may also involve communication with multiple stakeholders in a project, for example. It may involve gathering requirements from a marketing specialist, component manufacturers, and experts in the domain of operation of whatever the product will be. For instance, if we were to design an electricity metering application, then you would need electrical engineers who work in metering to be able to give their input in that design requirement. If, say, for example, we are designing a tracking system for cattle in agriculture, then obviously then we would need those agricultural engineers or scientists to assist. So this would be the domain experts. The process can also be very technical. For instance, it can be a process for gathering requirements specific to a certain hardware, where you would need to specify exactly the requirements of the hardware, or then you look at the software as well as the user interface. Now, multiple techniques, of course, exist for the gathering of requirements, which we will not cover in this text, but the whole process of requirement elicitation must give out as its output a concise and complete statement of requirements. The following step number 2, is the analysis. Now, the analysis step is whereby a compromise has to be reached between the long list of requirements which are wished for the system versus the realities which are put in place by constraints. For example, we may wish to design the best aeroplane. However, if the budget doesn't allow, the requirements have to be analyzed against whatever other constraints exist, such as cost and safety issues as well. And the analysis results in specifications, a list of specifications of the system. Now, these specifications can be given in any format. For example, there is an IEEE 29148 software requirement specification template, which can be used to specify this specification. The output, which are the specifications of the system, must contain, for instance, the project scope, the functions, the intended users, the operating environment, the likes of implementing constraints, user interfaces, software interfaces, communication interfaces which are there. In general, the system features and other non-functional requirements which might have been specified need to be listed as the output of this analysis process. Following the analysis, the first step of design begins. And the first step of design is called architectural design. Architectural design is first of all a high level design of the main components of the system. So it desires to specify mainly what the main blocks of the system would be. And it can be specified in many other forms as well. It could be in the form of a block diagram as indicated in this diagram. So this could be in the form of a block diagram which shows the main components of the system, whereby a microcontroller connects to the light sensor via an analog input, and then you see that there is again a remote screen which is connected by a UART, and there is a UV light which is connected by an analog output, and an LCD which is connected by multiple lines of digital output. So it can be as simple as this block diagram specifying the main components, the hardware blocks, as well as the the interfaces with which they are used to interface to link them. Now it can be also in terms of it can flow also a data flow in the form of a data flow graph. A data flow graph simply means the flow of information from one block to the next. This could be an example here of a smart light controller, which could be using information sensed from an LDR sensor, input via an analog potentiometer circuit, which is then linked to a block of analog to digital conversion, which will then be linked to a block of which goes through the microprocessor, and the microprocessor takes through the digital to analog converter, which controls the relay switch on how to switch on the LED luminance. So it could also, instead of just the block diagram as indicated here, it could also follow the flow of data in the form of a data flow graph. Remember now, this architectural design can also be specified both for hardware as well as software. So these blocks could also be blocks of software components. Another interesting way when a system has multiple components, another interesting way of specifying it is through the use of sequence diagram. A sequence diagram is such a diagram which shows the time interaction of the subsystems in a bigger system that may be required. In this case here, we have a banking system, which is represented by the bank server, as well as the ATM interacting with the user. So a sequence diagram is read from top to bottom, and it's a way of showing the interaction of different parts of the system, and it shows this using the exchange of messages, how each different parts of the system exchange messages in order to achieve that. The more detailed description of the sequence diagram would be offered in a later section of this presentation. But what you can see in this case is that the user interacts with the ATM by inserting the card, and then the ATM then requires a PIN, sends the message back to him. The user then sets the PIN to the ATM, but then happens that the ATM itself sends a message to the banking server to verify the PIN. If the PIN is valid, then the user is given the account information is also sent back to the ATM. So the ATM gives the user options, which the user then requests a statement, for instance, and then the ATM can then print out the statement based on the information that has been received from the bank. So this is also another type of high-level design that can be used in order to describe the interaction between different components of the system. The next set of steps is the detailed design. Now, the detailed design can be broken down into the design of the individual components, or it can be broken down into the design of the three aspects of the system. This can be the hardware design, the user interface design, and the software design. Once we have the high-level design, we can then now focus on each one of these disciplines to break down our design. So the hardware design can be as complex as a custom configuration of some hardware and sub-circuits. You may be wanting to design a custom processing system specific for that particular application. So it can be as simple as first selecting the microcontroller platform that we are using, which is the approach that we'll adopt in this course, and then selecting basically. In each case, the hardware design mainly becomes about how to select interfaces for different components that may need to, for the different hardwares that may need to then interact with the microcontroller, how to do pin assignment for your design, how to assign which outputs and inputs to what components, And then basically then the design largely becomes about designing of interfacing circuits or interfacing connections. This is an example here, for instance, of a voltage divider circuit where an LDR sensor is being hooked up to the ADC port of a microprocessor or a microcontroller in this case, of a microcontroller. So in this case, then the hardware design, part of the hardware design would be then to decide how much how much resistance would then be placed here, so that the LDR sensor can be read by the ADC in a predictable manner. The next aspect of a detailed design then would be to design the software. And the way in which the design of a software can be documented as previously stated, like hardware, it will be in the form of a block diagram. So where the main software components are listed as blocks, and the connection of how these components um, interact with each other is shown, or the data flow graph of how information flows from each block to the next as it's being processed by the system can be shown. So each one of these blocks can be a function, or it can be a big software component. Another way in which, over and above this, in fact, uh, each of those functions or algorithms which are implemented can be shown in the form of a flowchart, or in the form of a pseudocode, for instance. And so there are a variety of other UML diagrams that can be used, especially when the design is object-oriented. And such that can be used to specify the software design, such as the class diagram, the activity diagram. This of course diagrams we can read further about them, but for the purpose of this course, our design software design will just simply be detailed in the form of block diagram and or flowcharts. The last aspect here of a detailed design is to design the user interface. So the user interface can be specified well in a form of a mock-up design using what's called a wireframe. So this is an example of a wireframe. So remember, the user interface has to facilitate, it has to enable the user to be able to use the system. It has to offer functionality that's adequate for the user to be able to perform all functions that are necessary. Now, wireframes are a good way of communicating the design, in the sense that they design the layout of the system without emphasizing the visual design, without making it pretty, but they simply show the layout where each of these components will sit, or each of the interface features will be located. The design of a wireframe in this case, it has to have in mind the ability to function. So functionality has to be there in mind. And remember, the wireframe can specify a design which is either in software in the form of a web page, or a window, a software window, or it can be in the form of a hardware panel that has to be designed. Now, if the user interface has a number of other sub panels, it can also be drawn or indicated in the form of a hierarchy where, for instance, if this is a web page, you can have the main page, which indicates now how from the main page the user can traverse to see trends, can see a configuration page, can see also see an analysis page. The penultimate step is integration and testing. So the two steps go hand in hand. The process of integration is just simply means putting the components together. And as the components are being put together, there is a need then to ensure that they operate together to offer the required functionality as stated in the specifications. And of course, this is part of the testing where this this test of functionality will have to be done. So the process of integration and testing go hand in hand. And of course, it is likely that some or a lot of mistakes are going to be committed in the designing of interfaces between the subcomponents. And these mistakes will be discovered at this stage. And this can result into multiple redesigns or refinement of an existing design. So the straightforward process might have to be to go back to the architectural design for refinement, or it might also have to go back to the detailed design stage for refinement as integration and testing is being done. And the tests that are being done must be careful to test both for functional and non-functional requirements for completeness. Now, there are other more exotic ways of methodologies for design, which can be used depending on circumstances. You can have, for instance, a spiral model. A spiral model, it's an iterative process which uses mock-ups in order to gather more information about what the user requires. So the first batch of the system, they tend to assess the feasibility of the system. This is for high-risk projects where we want to test if the system is even possible. And using that system, the design team can then be able to, with the help of the user, derive known specifications and create further prototypes for their design. So the process of gathering requirements, designing, and integration and testing happens iteratively up until a perfect system has been established. It is worth noting that if there are too many spirals in this spiral model, then the time for the development could be very long. Another type of another methodology would be what's called successive refinement, and this is an incremental system. It's used to build systems which the project team is very unfamiliar with, and the system is built several times with increments each time with increasing complexity. So you will start first with the initial system, whereby in the initial system the requirements are gathered, the design is made, another detailed design is made, and there's integration and testing. Now, after that has been done, the system then is being refined in the next successive step through the same procedure again of requirement analysis, architectural design, detailed design, integration. So the system has been refined over and over successive steps up until it reaches closer to what the final project should look like. Another methodology is called hierarchical design. This can be used for an overly or an extremely complex process. So the design process is repeated, but each time is repeated over different levels of abstraction. So on the most highest level of abstraction, the whole process of gathering requirement specification, architectural design, and hardware design can continue. Now, as we get to a specific design of the hardware that we need, we can zoom into that and look at the detailed design all over again at a lower abstraction level or at a more detailed level. And then in that case, then we start first from the specification, specifically for the hardware, the architecture, specifically for that hardware. And then we design each of those individual modules for each of the hardware. We can also zoom again into those individual modules where we keep on designing the sub-components in a similar fashion. Thank you very much for your attention. Next, let us consider the documentation of the design in detail.